So, here is this is a function where it is one way. The m power e algorithm is still true, log e many computations are enough, because you can still keep squaring even in the modulo world, that is true. But when I want to compute, given m power e and e, I want to compute m, this is the discrete logarithmic problem, the best known algorithm take brute force time. So, inverse here is discrete logarithmic problem. Which is computationally hard. So, we are going to use these two functions. One is that you can take two large numbers and multiply, but factoring is hard, and you can take a message and take its exponent, which is easy to compute, but once I have the m power e, I can't compute m easily, that computationally these are hard problems. So, these are one way functions I got to address this second problem. Now, to address this key exchange problem, the first attempt actually was by Diffie and Hellman. They also won Turing Award. Okay, so, Turing Award is the equivalent of Nobel Prize. So, you have these one way functions which are very hard to break, but how do I avoid, and I want to convey some message to you, but there is this secret key which I do not want to convey, right. So, they were struggling with it and they came up with the following beautiful solution. So, let us forget exponential math and so on. So, let us say I have think of it, I have a costly object which I want to send it to you. I have a very powerful lock and key, nobody can break, because these one way functions are of that type. Okay. So, what do? I put that object into the box, lock it with my special lock and send it to you. Okay. But I have to give the key to you for you to open, right, and that is exactly the key exchange problem he wants to avoid. They came up, okay. So, how do I deal with that? How do I send the key? I need another powerful lock to send the key, that's just my strength. And then I have to send the key of that and all that. So, these one way functions are plenty, this powerful locks are there, okay, that you can lock it, an intruder cannot open it, because these brute force algorithms take exponential time to compute the inverse. Okay. So, they came up with this following cute method. Okay. So, I will put the key in, lock it with my powerful lock and give it to you, send it to you. Okay. What you do is you apply one more one way function, you put your lock on top of it, send it back to me. Okay. What do? I have the key for my lock, I will open it back and send it back to you. You have the key for your lock, you will get it, right. Very cute. It is like, but the problem is, so the key is never exchanged, the key never goes, key remains, the secret key remains with me, your secret key remains with me, we do not share it at all. Only thing is, it requires this couple of rounds. So, I put the lock, I put my object, lock it with my powerful key which nobody can open, you can't even open it unfortunately. What do? You put another lock, your powerful lock on it, send it back to me, I will open my lock with my key, send it back to you, you can open your key, right, and everything is safely sent under the assumption that nobody can open these locks because of these one way function assumptions, everything goes fine. So, what is it? So, what you are doing is, here is a message which I want to send, I apply a one way function on it and send it to you, right. You apply another one way function on it which is like f2 of f1 of m, send it back to me. I have the inverse function, so I will apply on it. So, the f1 will go away, on top of it now you apply your inverse function and what you get is m. Okay. So, this can also be mathematically modeled because these one way functions are there. So, if I want to send a secret message, this protocol will work. The only trouble with this is that it has to go through these multiple rounds. Okay. So, this was the first idea they came up with, and they were they almost had this avoiding the key exchange with one way functions. Okay. Now, Rivest, Shamir and Edelman came and combined these two one way functions and managed to give a protocol by which no key exchange happens and still the messages sent are secure under this assumption that these algorithms to factor or algorithms to do the discrete log are computationally hard. Okay. So, what is the RSA protocol? Okay. Which avoids no exchanges, no going back and forth. It is like, think of it's sort of like a user ID and password, right. You publish your user ID to the whole world, no problem. You say this is my email address, right, and I send messages to you, but only you can see them using your password, right. Nothing gets exchanged. In fact, you put your user ID public, and that's the kind of philosophy you're going to have. There will be a public key and a private key. Okay. My public key will be in my website, anybody can see it, but my private key is secret. Okay. You use my public key to send messages to me. I use my private key to see this. Nothing, the keys don't get exchanged at all. What are this public key and private key? We'll get to that. Okay. So, here is the RSA system, how you build it, right. Take two large prime numbers, P and Q, and multiply them. So, this is all happening in my end, okay, no exchange, no channel communication, nothing is happening. So, this is something I can do. Have you guys seen this notation phi of n? Euler phi function, you know what it is? Yes, what is it? Yeah, number of numbers less than n co-prime to n, they do not divide n, right. This is basically number of numbers less than n that are relatively prime. So, they do not divide. So, for example, if n is 24, then what are the numbers which are relatively prime to n? Well, there is 1, 5, 7, even not 9, okay, 11, 13, 17, 19, 23. So, 1, 2, 3, 4, 5, 6, 7, 8. So, phi of n will be 8. Okay. So, number of numbers that have no common factor with n. So, what is phi of n if n is equal to p times q? Yeah. So, there is a simple formula which we can verify that it is p minus 1 times q minus 1. So, the beauty of this whole system is it uses some very simple number theory and these two one way functions, which I already described. That is also very easy to describe. So, the second step is choose an odd number e such that e and phi of n are relatively prime. Okay. So, e is relatively prime. So, just find some, there are p minus 1 into q minus 1 numbers which are relatively prime to n. Sorry, no, it should be relatively prime to phi of n, not to n. Choose a number e such that e and phi of n are relatively prime. Okay, this is some simple steps. So, you just go through numbers less than phi of n, p minus 1, q minus 1, and see, find a number, some odd number that does not divide this. I mean, there are enough primes that any prime will have no common factor with anything else anyway. So, it's easy to find and find this. Okay. So, my public key would be E and N. I will tell the whole world, if you want to send message to me, use this E and N. I will tell you how to send the message, what this function f is, I will come to that, but this E and N becomes public. Now, because E and phi of n are relatively prime, again, so you can find the GCD of these two numbers, and if the GCD of two numbers A and B is D, then you can write D as a linear combination of A and B, x and Ax plus By equal to 1. So, let me write this and then come. So, there exists a D such that E times D is congruent to 1 mod phi of n. Because E times D plus some f times phi of n would be equal to 1 mod phi of n. So, f times f of n phi of n will go away. So, E times D equal to 1. Okay. Another way to see it is that these numbers which are relatively prime to a number, they form a group under multiplication modulo that number, and so if E is such a number, D would be the multiplicative inverse of that function, that number. Okay. So, and how do you even show a multiplicative inverse exists using this GCD algorithm and the fact that you can write the GCD as a linear combination of these two numbers. So, now you can, there is a D such that E times D is congruent to 1 mod phi of n. The D is my secret key. Nobody knows, the D is the secret key. Okay. That is all I will do. So, what do? I do all this steps 1 and 2, find some two large prime numbers, multiply, compute my phi of n, choose such an E, and then go tell the world this E and N is sort of like my user ID. D is like my password. I won't tell anybody, it is secret to me. Okay. So, now anybody who wants to send messages to me, what do? Okay. Now, encryption. If you want to send a message M, what they will do is compute, they want to send a message to me, right. So, they will use my encryption. So, you may have done something like this in your website and you would have published your E and N, she would have done something. So, if I want to send message to her, then I will take my message M, raise it to E, her public key, because that is available in the website, mod n. N is also available. So, this is the encrypted message. This is the one way function, and I already argued that, but I did not argue, but I just sort of told you that if somebody knows m power e, it is not so easy to get m, because it is exactly like the discrete log function problem. So, you need to actually try one by one kind of thing. So, this is m power e is like some number, okay. It just goes some 1030 digits number which goes through the channel, okay. And I even tell you it is exactly m, it is actually some message power u, but nobody including you can just from this can get message, but you have to get your message, you have to get the message. So, what do? Well, you have a secret key, remember. So, decryption. So, this is a easy one way thing which goes through and I can easily compute it. The decryption will get m power e and they will apply their secret key and raise it to power d. Okay. Now, this is basically, this is all in the modulo n computation, m power e d. What do I know about E d? 1 modulo phi of n. Okay. Now, there is a nice, again cute little theorem, Fermat's little theorem, which tells you that if your power is 1 mod phi of n, then ed is congruent to 1 mod phi of n, and m power ed is nothing but m mod n. Okay, so this is because ed is the order of the group. Okay, your group has phi of n elements. If you are familiar with the little algebra here, phi of n is the size of the group. So, if you take your m and raise it to some multiple of phi of n minus 1, right. Fermat's little theorem says that any a power phi of n minus 1, no, phi of n, sorry, a is congruent to a mod n. Ed is actually 1 mod phi of n, it is not a multiple of phi of n, it is a multiple of phi of n plus 1, good, right. So, ed is some m power phi of n times m power phi of n will, some multiple of phi of n will become 1 and the m will remain, and that is, isn't that what I wanted to get, because from this encrypted message. So, what is the encryptor's job? This is the message you want to, and you want to send to her, take her public key, raise it, take mod n, that is also sitting in her website, and then you send it to her. And what does she have to do to retrieve the message? She has a secret key, this is like the password, nobody else knows. So, I raise it to power of d and I get my message, do mod n and get my message. Okay. So, this is it, very cute, no key exchange. Basically this E and D are all happening in my website, and I publish E and keep D, that is it, exactly like the user ID password thing. Okay. And now different people can have different E's and D's. So, whoever I want. So, a bank wants to send something to you. So, each one will have their own E and D, and then I can communicate this way. Now, suppose I am able to factor n, right, then this I can compute p and q. Then I know this phi of n is p minus 1, q minus 1. So, once you give me E, I can actually compute D also. If you have if I know the factors of n, because n is known, if I know the factors of n, I can compute phi of n, because phi of n is exactly p minus 1 into q minus 1. So, if you know if you can factorize it, I can compute phi of n. If I can compute phi of n and you gave me E is public, I can compute D. So, if factoring is easy, then this system can be broken, because once I know D, whatever the retriever does, any intruder can do that as well. So, basically if factoring can be done fast, then RSA can be broken. But the converse is still not known. Maybe there are other ways to factor RSA, even if you do not know a fast algorithm to do factoring. And also, there is this notion of digital signature. Right. So, where the message is not really secret, okay. It is like a check. Imagine I am giving somebody a check. So, the check is open, it is not secret, but there is a signature which needs certain authentication. How do you know that you have a certain signature and you have to verify that this signature is mine? Okay. How do you verify that? Well, here is a way to do this, you can use this, right. So, what I do is I send my message and send m power d. D is the secret key only I have, you do not have it, right. So, the m power d nobody can create, anybody who has only d can create this. M power e everybody can create, because my e is public, but m power d only I can create, right. So, I send these two to you. M is not a secret, so no problem, it is like a check, and m power d is the signature, I send it to you. How do you verify that it is actually my signature? You power what? E. You raise it to, anybody can verify this, because E is public anyway. So, you raise it to power E, whatever that is coming, and you verify that is actually equal to m, then you know that it must have been come from me, because you look at my E and then you raise it to, so m power d power e is, if then you know that signature verified, right. That's it. So, very simple proposal, I know, something which is understandable to a third year, second year student. We provide some algorithms, little number theory, factoring. It has far reaching consequences. So, of course, to really make it usable to public and so on, it required a lot more engineering and optimization, and that's what they have done. So, this Rivesh, Samir and Adelman formed a company, and there is something called pretty good PGP, pretty good privacy, if you have heard it. To the extent that every website, every transaction has a certain version of RSA underneath it, that now there are also now crypto systems based on other hard problems. So, in number theory itself, there is something called elliptic curve cryptography, where you move to some higher level of security. Okay, I don't know much, so I won't say much about it. But this is a fascinating story. I mean, I think there are very nice popular books on about this RSA crypto system. So you should just try and read and understand, because I know how they developed the whole thing. And yeah, okay, I think that's it.